All right, so far in statistics, chapters 1 through 5, we've talked about descriptive statistics, okay? So for example, how to collect and describe data, and probability, so how to find probabilities and analyze discrete and continuous probability distributions, okay? In this chapter, starting with chapter 6, we begin dealing with inferential statistics, okay? This is the second major branch of statistics. Inferential statistics is more of what we can infer from the data that we're given. That's why it's called inferential statistics. Okay. Now, somebody earlier said, so it's like assuming. Well, kind of, but inferring something has more of a positive connotation than assuming does. Okay. So we're going to take the information that we know and we're going to figure stuff out from it. Okay. There's an example listed here I wanted to talk to you about a little bit. Just because I want you to see that some of this is fairly logical that we're going to be talking about in this chapter. Okay, so there's a chess club that wants to estimate the mean IQ of its members. The mean of the random sample members is 115. Okay, that's the mean of a random sample. Because this estimate consists of a single number represented by a point on a number line, it's called a point estimate. Does that make sense? A single number on a number line is a point estimate. The problem with using a point estimate is it's very rarely equal to the exact parameter or the exact mean or standard deviation or proportion of that population. In this case, the standard mean. Okay? So in this chapter, we're going to figure out how to make more meaningful estimates by specifying an interval of values on a number line, together with a statement of how confident you are that your interval contains the population parameter. So for example, let's say we want to be 90% confident of our estimate. Okay, so here's what we would do. Well, we know the mean of the random sample. First of all, it told us that. Okay, the mean of the random sample is 115. Well, first of all, we have to find the margin of error. We're going to talk about how to find that today. Right now, they're just telling us E is 3.3. Okay, it's never just, hey, let's choose a random number. How about 7.6? How about 2.1? Okay, there's a way to find that error. Okay, formula, in fact, that I'll show you here in just a little while. Once you find the margin of error, take the mean of the random sample that you figured out and subtract it and add it to that mean. Take the error and subtract it and add it from the mean, and then you get an interval, the low point and the high point that it probably is in. Now, does that seem fairly logical? Yeah, we've done similar stuff to this, not exactly, but we've done similar stuff to this in other classes, yes? Okay, so that's kind of what we're going to be talking about. So a statement that would talk about this this interval right here is right down here. It says, so the club can be 90% confident that the mean IQ of its members is between 111.7 and 118.3. All right, so here's that definition I was talking about of a point estimate. Point estimate is a single value estimate for a population parameter. The most unbiased point estimate of a population mean is the sample mean. All right. Now, the validity of an estimation method is increased when you use a sample statistic that is unbiased and has low variability. Variability, the amount that it changes, right? Okay. The statistic is unbiased if it does not overestimate or underestimate the population parameter. In Chapter 5, we learned that the mean of all possible sample means of the same sample size equals the population mean. So as a result, the sample mean is an unbiased estimator of the population mean. When the standard error, remember we talked about this, the standard deviation divided by the square root of the number of terms in the sample? Remember that formula? Okay, when the standard error of a sample mean is decreased by increasing n, it becomes less variable. It's very important to me that you understand this sentence. Okay, so let's think about this. When the standard area is decreased by increasing n, what happens when I increase n? The denominator gets bigger, right? And when the denominator of a fraction gets bigger, what happens to the value of the fraction? It gets smaller, right? So does it make sense that when the standard error is decreased, So when this gets smaller, by increasing n, it becomes less variable. When this is smaller, it's going to change less, isn't it? Okay, does that make sense for that sentence? Okay, so example 1. Example 1 is kind of important right here because example 2 actually goes from example 1. Okay, so let's make sure we understand about example 1 right here. An economics researcher is collecting data about grocery store employees in a county. I kept saying country earlier, and there's no R in this word, so it's county. Okay, the data listed below represents a random sample of the number of hours worked by 40 employees from several grocery stores in the county. Okay, now is this 40 right here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is, right? That's 40 values. Is that the population? No, it's the sample, right? This right here is a random sample of the number of hours worked by 40 employees. Is everybody okay with that? Okay. So find a point estimate of the population mean. Well, first of all, you know that the population mean is going to be equal to what? The sample means, right? So if I can find this mean right here, that'll help me figure out the population mean, right? Okay, so the sample mean of the data is the sum of the x values divided by the number of terms. Well, isn't that how you find the population mean too? Yeah, but we're just given the sample mean, so we're going to go with it. The sum of this is 1184. There's 40 possible terms here, so that averages to be 29.6. So the sample mean is 29.6. So the point estimate for the mean number of hours worked by grocery store employees is 29.6. Is everybody okay with that? That seems familiar with what we did last chapter already, right? So good. That's good so far. Okay. But here's the thing. We need to be able to make an interval estimate. We talked about that in the this first example with the chess club right up here. Okay, but here's like the real mathematical way to do this. Okay, it's not just a guess, it's figuring stuff out. Okay, an interval estimate is an interval or range of values used to estimate a population parameter. Okay, so you can assume that the point estimate in example 1 is not equal to the actual population mean, but it's probably close to it. All right, so to form an interval estimate, use the point estimate as the center of the interval, and then add and subtract a margin of error. They're telling you right now, if the margin of error is 2.1, so we're not quite to figuring out how to find a margin of error yet, just giving you another example of what we talked about earlier with the chess club. If the sample margin of error is 2.1, we want to take this 29.6 and add 2.1 to it to get 31.7, and we want to subtract 2.1 from that mean to get 27.5. Okay, this gives us our interval estimate. We think most likely our actual population mean is going to be in this interval. Got it? Questions? Okay. Before finding a margin of error, you should first determine how confident you need to be that your interval estimate contains the population mean. So here is a really important thing, a level of confidence. Okay? Now, if I ask you how confident you are that you made an A on your test, if I haven't told you the grade yet, you might tell me things like kind of or sort of or absolutely certain that I got 100, right? But in this case, confidence levels are going to be values. They're going to be numbers. Okay? And most likely we're going to talk about like 90% or 95% or probably not 50% because that's pretty low, right? We want to be very confident. So our confidence levels are usually going to be pretty high. Okay? Now, keep in mind, if we give it 2%, you know you're eventually going to have to change that to a decimal because that's how we work with values like that. Okay? So here's an example. First of all, let's talk about the definition. Okay? The level of confidence is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. Why do we want it to repeat it a large number of times? Because it's more likely that it's right. Yeah? Yeah? Okay. you know from the central limit theorem that when n is greater than or equal to 30, then the sample distribution of sample means is a normal distribution. Do you remember us talking about that? Okay, so the level of confidence is the area under the standard normal curve between the critical values. So all that stuff that we did last chapter of finding the area underneath of a normal curve suddenly has meaning. Okay, now we know why we're doing that. We're doing it because now we can find critical values. Now we can figure out level of confidence. Now we can find an interval estimate of all sorts of different data. Okay, so chapter 5 was really like, okay, I have to teach you how to do it so that when we get to chapter 6, I can show you why. Okay? All right. Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. Okay? You can see from the figure below, right down here, that C is a percent under the normal curve between negative Z sub C and positive Z sub C. The area remaining, this stuff out here, is 1 minus C, so that each side of this is half of 1 minus C. Okay? This table right here was really helpful when the guys last period started working on their homework. Okay? So if you're looking at your textbook, make sure you mark 299. If you're looking in your on your computer, make sure you kind of keep that page number in your head as well to go back if you need to refer back to this page number. It's on page 299. Okay, if you need to refer back to this chart. Okay? So let's make sure we understand this. Okay? 90%, see our confidence level is 90%, so our C value is 0.9. Yes? So our C value is 0.9. That's the blue region. Okay? Now 1 minus C would be 10%. If 90% is under the curve, does that make sense that 10% is left over? Now it says it's a yellow region, and maybe my eyes are just not working, but that does not look yellow to me, but I'm not judging it. Okay? We're going to go with yellow. Are you okay with that? Okay, so half of that value, half of 1 minus C value should be in each tail. You okay with that? Okay, so the critical value is going to be negative Z sub C is going to be negative 1.645. Where in the world did negative 1.645 come from? Any ideas? I'm going to go look at my table. 1.645 is pretty close to in between these two right here, right? So that would be 0.05. Well, we've already decided that 0.05 is how much is in each tail. Remember that? So that's where that negative 1.645 value came from. And it goes to 3 decimal places, even though all these things on the side and the top go to 2 decimal places, because in this particular case, the value that we're looking for, the 0.05, is exactly halfway in between these two values. Remember us talking about that before? Okay, if it's not exactly halfway in between, we choose the closer one, right? But if it is exactly halfway in between, I use the negative 1.6, and then halfway in between these two is 0.045. You okay with that? Okay, so that's where that value came from. But you also know several things. Okay, you know that this is symmetric. So if you know that the negative Z value is negative 1.645, what's the positive Z value? Positive 1.645? Yeah? Okay. Now we could look that up if you wanted. And we do. 1.645. What value is this? 0.95? Where in this problem does it talk about 0.95? Well, 90% is the C value, right? Our confidence level. But if I know half of the 10% is over here and half of the 10% over here, isn't everything to the left of this 95%? Yeah, so do you see why I looked up 95 or the 0.95 here on the table? Does that make sense? Okay. So that's going to be something you really want to refer back to, especially when you're working on your homework, because several of the questions ask about this. Okay? Everybody okay so far? Awesome. Next definition we need to talk about is margin of error. Now it's finally time to figure out what that E value is. Okay? The difference between the point estimate and the actual parameter value is called the sampling error. Okay? When the mean is estimated, the sampling error is the difference, the population mean and the actual mean. Okay? In most cases, of course, the mean is unknown and the sample mean varies from sample to sample. However, you can calculate a maximum value for the area when you know the level of confidence and the sampling distribution. Okay? Now, some of these things in here in this particular formula, I hope you recognize. Do you recognize anything in this formula right here? Yeah, this part right here, right? Standard deviation divided by the square root of the number. We actually talked about that just a second ago when we talked about sample error. That's from last chapter, isn't it? Okay. The standard error, I think I said sample error, but I meant standard error. Sorry. The standard error is the standard deviation divided by the number of terms in the sample mean, the square root of that number. Okay. All we're doing now is multiplying it by that Z value. So it's something we already know how to do, a sample error, standard error, excuse me. This is giving us the margin of error by taking the Z value of the confidence level and multiplying it by that standard error. Okay, so again, this is something that you've already seen. We're just adding one more thing to it. But here's the deal. Two specific conditions have to be met for us to even be able to use this. First of all, the sample has to be random. It can't be a hand-picked sample. It has to be random. Second of all, one of two things has to be true. Either it's normally distributed or our N value is greater than or equal to 30. So if we think back to example 1, would it fall in these parameters? Is this a sample? Excuse me, is this a random sample? Well, yeah, it tells you that it is. Okay, you can trust that, the words in there. Is it either normally distributed or is the N greater than or equal to 30? It's more than 30, right? It's 40. In fact, it tells us. So we don't have to worry about it whether it's normally distributed or not because our N value, our number of terms in our sample is greater than 30, greater than or equal to. Okay? So example 2 talks to us about using this example 1 and finding a 95% confidence level to find the margin of error for the mean number of hours worked by the grocery store employees. And it does tell us the standard deviation. Could we do this problem if it didn't tell us the standard deviation? No, we could not. Okay? First of all, that's part of our formula, isn't it? Okay? So, because the standard deviation is known, in this case specifically 7.9, the sample is random, and our N value is greater than or equal to 30, and it's in fact 40, we can use this formula that they just gave us to find the margin of error. Okay? The Z-score that corresponds to a 95% confidence level is 1.96. So here's a problem that happened earlier. Okay? If I'm going to look on this chart right here at 1.96, because it gave me 1.96, the example did, now the problem's not going to, that does not say 95%. And so the question is, how did they come up with this number right here? How did they come up with 1.96 because when the other person said, when I searched 0.95, it was right here, which means it should be 1.55. Excuse me, 1.655. Well, my question is this, were they looking for the right thing? Remember that if this is my graph right here, and I want 95% underneath, how much is left for out here? So 5%, right? 5% is left for out here. So how much is left for this right tail over here? 2.5, right? Half of that value. So how much is to the left of that value? 97.5. That's where that 97.5 value comes from. Does that make sense? So then when I go and look on my table for 97.5, right here, that's where we get 1.96. Oh, you couldn't see any of that. I'm sorry. 1.96. But you know how to read this table, right? Okay. So that's where in the example they got 1.96. Are you okay with that? All right. This implies that 95% of the area under the standard normal curve falls within 1.96 standard deviations of the mean. Okay? So use those values that we just found then. Here's z sub c, which is 1.96. Here's the standard deviation, which they told us. And here's the number of terms, which is 40. Guys, now it's just arithmetic, isn't it? Plug it into your calculator to find a value. 2.4, but it's also important to know what that means. 2.4 what? Okay? So the interpretation, that's the sentence that's our solution. It says you are 95% confident that the margin of error for the population mean is about 2.4 hours. Does that mean that they worked 2.4 hours in the store? That means that our margin of error is 2.4 hours. So plus or minus 2.4 hours from whatever that mean was, which we know was 29.6. Okay? So we could find, if we added 2.4? If we added 2.4 and subtracted 2.4 from here, that would give us our interval estimate. Does that make sense? Where all those things came from? Okay. Excuse me. So, confidence intervals for population mean. It's kind of what I just did without telling you what it was, but we kind of talked about it already, so it's just now the fact that there's a formula. When you know the mean, like in that last problem was 29.6, to find the confidence interval, we take the mean minus the error. The sample mean minus the error, sample mean minus the error, and the population mean has to be between those two values. That's what I was just saying. If you take the 29.6 and add the 2.4 and subtract the 2.4 from it, that will give us our confidence interval for our population mean. Does that make sense? Okay. So these guidelines are pretty dang important when we're talking about constructing confidence intervals for a population mean. Okay, let's talk through it. You already know how to do it, but let's talk through all the steps, because sometimes I know for some of you it helps to have some steps to go by. Okay, so number one, verify that you know your standard deviation. Verify that the population is random. That the sample is random, and that either the population is normally distributed or n is greater than or equal to 30. What happens if one of these is not true or known? You stop. You got to stop, right? You can't go any further because we can't use the margin of error value unless these are true. Okay? So first of all, find the sample statistics, the number of terms, and the sample mean. And then they reminded you right here what the formula is for sample mean. Then find the critical values. So it says use table 4 in appendix B. Well, that's just our z table, right? That's this table right here. You okay with that? You guys are getting pretty good at reading those. Find the margin of error. Here's the formula to find the margin of error. Once you know this z sub c, the critical value right here, you know your standard deviation, you know your number of terms, it becomes just arithmetic. Okay? Last but not least, find the left and right endpoints to form the confidence interval. Take the mean that you know, subtract the error, and add the error. That gives you the left endpoint and the right endpoint, which gives you the confidence interval. Does that make sense? Okay. Now, there's 3 examples. The first one we've actually done. We've actually already talked through it. That was the taking the 29.6 and subtracting the 2.4 and adding the 2.4 to get the actual confidence interval of our example 1 problem, the grocery store hours one. Okay? Any questions about that? Let's talk about real quick about the interpretation, the sentence solution of our problem. With 95% confidence, we can say that the population mean number of hours worked is between 27.2 and 32.0 hours. Everybody understand where that sentence comes from? Okay, excellent. Example 4 and 5 in your book, same kind of thing. Okay, same kind of thing. It gives you the standard deviation. This one specifically talks about the calculator. It's an 84 though, so we don't have instructions for that. Okay, but you can at least look through those words and talk about the standard deviation and things like that. Here, another, constructing a confidence interval. It tells you the standard deviation. You can find the z-score. Tells you the number of terms. It tells you the mean, even, and you're just plugging stuff into a formula. Make sure it's in the right place, things like that. Okay? And then you're finding the left and right endpoints to find that interval, the confidence interval. All right? Last thing here in 6.1, it talks about a sample size. Okay? If you take this error formula, you might be asked for a minimum sample size. What's the smallest number of sample size that I can get to be able to estimate the mean? Well, if you take this formula for error and solve it for n, guess what you get? The smallest sample size, the minimum sample size. It'll solve for n, which will give you the minimum sample size. So I don't want you to think this is a total another formula that you have to memorize or something like that. It's just your error. Let me show you real quick. It is your error of margin of error, excuse me, not error of margin, the margin of error formula solved for n. So you're going to take your z-score, your standard deviation, and your error, divide those numbers, square it, and that should be your minimum sample size to be able to estimate your population mean. Okay? Any questions?